In this video, we're going to talk about one sample t-test. If you recall from chapter 4, we did inferences for one population mean, and in that chapter, one of the assumptions that we made was that the population standard deviation sigma was known. Okay, now we're going to make a change to that assumption. Now, when that was the assumption in chapter 4, we actually used what we called a Z procedures for confidence interval and hypothesis tests. So what we're doing in this section actually is making a change to that assumption. So what if the what if the population standard deviation is actually unknown, which is more realistic case? And how is that going to affect our procedures? Well, it turns out that when that is the case, then rather than using a normal distribution, we're going to use what's known as a student's t-distribution, or simply we call that a t-distribution. Now, a t-distribution, by the way, more specifically, we're talking about what we call a central t-distribution. In the case of a central t-distribution, the center of the distribution is always at 0. Okay, in other words, the mean of this probability distribution is going to be 0. We also have a non-central version of it, but that's beyond the scope of what we're doing here. Okay, so that's going to be the difference in our procedures. We're going to switch to a T procedure rather than a Z procedure. So here I have a little note for you, that if you're not given the standard deviation and if you use a sample mean, then in that case we have to use a T procedure. Okay. Now, something I just kind of interjected my own personal experience, something that I've learned that works out really nicely, is that oftentimes you may wonder, well, should I use a T? Should I use a T distribution or a Z? Well, if you always use a t-distribution, I think you're erring on the side of the caution, and most of the times you're going to be right using this, because oftentimes you don't know sigma, you're collecting sample, and you do everything based from the sample, and that right there tells you need to use a t-distribution. Also, even if sigma is given to you, which again, more realistic case is that you're not given sigma, the population standard deviation, and if you use a T procedure, when the sample size is large, it turns out that it really doesn't make a difference. And the primary reason for that is because for large samples, a T distribution actually approaches a standard normal distribution, as we will see in some of the sketches that are coming up. Now, just to kind of historical note, here's the gentleman that actually came up with the distribution. William Silly Gossett, and you can kind of do a Google search. I got this from Wikipedia, and you can kind of read about this. It's very interesting history behind this distribution, and that the reason it's called the student's t-distribution, as I have it earlier up here, I refer to it as a student's t-distribution, is because this gentleman, William Silly Gossett, he was working for Guinness Brewery, okay, and his employer would not allow him to publish his work because of conflict of interest, so he would still like to do so. So oftentimes he would submit his papers to Biometrica. I believe that's the institution that he was using. And he was sending his papers to Biometrica under the pen name student anonymously. So hence it bears the name student's t-distribution. So again, if you're interested in that, you're welcome to read about it. And so what does this t-distribution look like? Well, here I have a sketch of several sketches of a t-distribution. And you can see it in comparison with the standard normal distribution here, and highlight it in yellow. That's the standard normal distribution. That's normal 0, mean 0, deviation 1. And what you have in green and blue are a couple of t-curves or t-distributions. Now this is again a probability distribution, and the parameter of this distribution is degrees of freedom. That's what it's called. So in blue you're looking at the t with 1 degree of freedom, and this one is what do you call it? Actually the highlight, I apologize. The highlight is, the yellow is a t with 6 degrees of freedom. The green is what the standard normal is. And you can see the primary difference between a t and a standard normal distribution for low degrees of freedom, that means the small samples for us would be, is primarily in the tail end of the distribution here. You see, a t distribution has what we call heavier tails, means more data lies in both tails of the distribution. Okay, so there you go. There you have the general shape of the distribution. There's a complicated formula for it also, which we don't need to tell you about it. You're welcome to look at it from again on Wikipedia or other resources actually have it. Now some of the properties of this t distribution, I have it listed for you in this table. I'm going to read it with you. The first property is that the total area under the t-curve must be 1. And the reason for this is because this is a probability distribution. So the area under the distribution, in the case of continuous probability distributions, which is what normal, t, and so forth are, those probabilities, remember, they're synonymous with area under the curve. So that's why the area has to be 1. The second property is that the t distribution goes indefinitely, just like the normal, in both directions. In other words, this t stretches on all the way to negative infinity and all the way to positive infinity, although you can see that rapid drop-off, which converges towards the number line rather rapidly. There is a symmetry with respect to the center, the 0. So that means the median is also at 0. The mode is also at 0, just like the normal distribution was, standard normal. And that, importantly again, as the degrees of freedom increases, the t distribution actually overlays with a standard normal distribution. So that means its standard deviation approaches 1 as degrees of freedom increases. Okay, but for low degrees of freedom, its standard deviation is actually slightly bigger than 1. And here are again several other t distribution, t curves. The one that's actually in black, right in here, this one has the highest peak. Notice that's here again, I use Wikipedia on this one, and this is Greek nu. NU, just like mu we had MU, this is Greek, and nu looks like italicized V. So you're looking at a t again with 1 degree of freedom to 5 infinity. So it goes from here 1, 2, 5, infinity. With infinite degrees of freedom, you actually have reached standard normal distribution. Okay, now what we want to do again in this segment, we want to do hypothesis test, we want to do confidence interval for population mean. So the procedure is known as one mean t interval procedure. This is the confidence interval for mu. And these are the assumptions, the basic assumptions we have, that we have simple random sample. The population must be normal or large, and large here means at least, let's say normal population or large samples, that is. That means at least 30. Okay. And sigma must be unknown here. Okay. So if sigma is unknown, again, we're going to use the sample standard deviation for this. And this is the formula, but we're not going to do this by hand. I just want to show you the formula. We've seen a comparable formula when we looked at a z interval procedure earlier in chapter 4. So, but we're going to get things from Minitab. Okay. So this is how the confidence interval is constructed, and it's going to be exact. This confidence interval will be exact if the distribution, in fact, the parent population has a normal distribution. Otherwise, it's approximate. And with that, for the confidence interval, actually, and the hypothesis test, I don't have it, but we're actually going to do a hypothesis test also. Remember, we use p-value method for hypothesis tests. So what I've done is I actually picked an exercise from your textbook that we are doing, that open intro textbook. So in this exercise, we have fueleconomy.gov, the official U.S. government source for fuel economy information, allows users to share gas mileage information on their vehicles. Apparently, you can go to the site and you actually input yourself the MPG, the miles per gallon, your gas mileage yourselves. The histogram below shows the distribution of gas mileages in miles per gallon from 14 users who drive a 2012 Toyota Prius. I believe that's the hybrid model. The sample mean is 53.3 miles per gallon, and the standard deviation, remember from the sample, that is, turned out to be 5.2. We don't see the data here, these 14 numbers, so we have summary information. We know the sample size, we know the mean, we know the sample deviation. We call those summary statistics. Now, there is a note here. It says, note that these data are user estimates, and since the source data cannot be verified, the accuracy of these estimates are not guaranteed. Okay, so you can kind of see pretty much like a normal distribution. Now, we don't know again how this sample was drawn. So in part A, the question, we would like to use these data to evaluate the average gas mileage for all 2012 Prius drivers. Notice how inferential that is. When you're doing this for every Prius automobile, for all of them, then it becomes inferential statement. It means you generalize to the population. Do you think this is reasonable? Why not? So, well, let's see. I put no for a couple of reasons, because this is not a simple random sample. You know, I own a Prius and I didn't even know about this site. So my information isn't there. So not everybody knows about this site. So it's not really a simple random sample. And the second thing is that the sample is too small. You know, for 14, that's too small to make that inferential statements. So realistically, I don't think it's reasonable. But then again, you can make a case where, well, although it's a small, nevertheless, it's a sample, better than nothing. In part B, the EPA claims, so notice we want to test the hypothesis here. There is a claim. They claim a 2012 Prius gets 50 miles per gallon, and that's city and highway combined. Do these data provide strong evidence against this estimate for drivers who participate on fueleconomy.gov? So one thing we could do to make this more valid is that we can say that we are inferring to the population of those that actually go on that site. Then that would be more legit than implying this to nationwide figures. Okay. So this would be a representative sample from that site. Therefore, we can infer it to that target population of all the cars, Prius, that are listed in that site. Now, note any assumptions you must make as you proceed with the test. Well, the assumptions are listed up here. Assumptions 1, 2, 3. That we have simple random sample. In this case, we don't have a large sample. We only have 14, right? So the assumption is the normality of gas mileages. And of course, sigma is unknown. So the normality, again, you can see it by the histogram. That seems reasonable. So I have the null hypothesis stating the average is 50 miles a gallon. And we want to do this because the question reads, do these data provide evidence against the estimate? The estimate of 2012 that's what EPA claims. So that they're going to become the null. That's the status quo. So the research is going to say that the average is different from 50. And notice it's a two-sided alternative. It doesn't say more or less. It just says different from. And the sample was 53.3 up here. So it looks like the average is higher than what the EPA actually estimates. Okay. And in part C, we want to calculate a 95% confidence interval for the average gas mileage. Okay. Now, one thing about part B, by the way, is that notice we are not given the size of our test, the alpha, the significance level. The question is do these data provide a strong evidence? So what do we mean by strong evidence here? Remember, strong evidence means p-value less than 0.5. P-value less than 0.5 means a strong. Less than 0.1 is a very strong, and then you have different strength, degree of strongness as p-value gets smaller and smaller. So here are the assumptions I have. Assuming normality of MPG and of course a simple random sample, because sample is 14, so I cannot say assuming sample is large. Now the p-value, and I'll show you from Minitab how I got that one. But the p-value here turns out to be 0.034. So because p-value is less than 0.5, we do have a strong evidence against the null. And again, it seems like the average is actually about 53.3. Okay, and here is actually the hypothesis run, the one sample run from Minitab. Okay, so looking at this output from Minitab, first of all, we get to see some descriptive statistics. So notice here's the sample size. Although it says capital N, we know this is little n for us, right? That's the sample, not the population. Here's the sample average, 53 miles per gallon with a deviation of 5. And the standard error, that would be like your sigma over square root of n that we had in chapter 4. Except we don't know sigma, so if you get 5.2 divided by square root of 14, you get that number. And here's a 95% confidence interval for the mean. Anywhere between just above 50 to 56. Remember, if 50 was inside of this confidence interval, then we would not reject the null hypothesis at alpha 0.5. Because that's got to be the other side of that 95%, because 0.5 and 0.95 add up to 1, or 100%. And here's the formal hypothesis test. This is a two-sided alternative. Our test statistic turned out to be 2.37 for a p-value of 0.034. 0.034, so we're not going to reject this null hypothesis. And I'll go and show you how to do this in Minitab in a moment. Now, again, we did reject the null hypothesis. So this is the p-value is the actual probability of a type 1 error. That means we rejected the null, and we said, remember right up here, we mentioned that there's a strong evidence against the null. We could still be making a mistake when we made that statement. We should not have rejected it. The probability, the actual observed probability of a type 1 error is now 34 in 1,000. Again, that means 34 in 1,000 chance of falsely rejecting the null when we shouldn't have. That's the probability of a type 1 error. Okay, so now let's go to Minitab and actually run this information. So remember, the sample size was 14. The mean was 53.3 and the standard deviation was 5.2. Okay, we know those information when we go and we want to do a 95% confidence interval and a two-sided alternative. Okay, so let me go. I already have Minitab. Let me actually do this. I'm going to run the Minitab and you will see. Okay, should be up and running. I thought I had it running already. So this is what Minitab is. I may have to change my window here because let me actually pause and enlarge this window to contain all of my Minitab viewing window. Okay, so here I adjusted my viewing window. So let's actually do this in Minitab. So in order to test that, to do a t-test, a one sample t-test, we're going to go to Stat, and let's go to Basic Statistics. Then we're going to go down here. You see one sample T instead of one sample Z chapter 4. Now we're doing a one sample T test here. Click on that. Now one or more, let me drop this. Do we see the data? We don't obviously have the raw data, the raw scores. We didn't see those 14 scores. So we have summarized data, summary statistics. The sample size was 14. Going to type in the sample size. The sample mean turned out to be 53.3, and the deviation was given to be 5.2. And we're going to perform a hypothesis test. The hypothesized average was 50 according to EPA. And in the options here, this is where you designate the type of alternative. We had a two-tail alternative. And our confidence level, we're going to keep it at default 95. That's what that problem called for. Hit OK. And that's it. Hit OK again. And there you have it. And these are the numbers that I got. And you saw it in my note. I got them exactly from this output. So, with that, we are done with this section. And let me go back to my note. And just to show you, okay, I guess I could resize my window here again. Anyways, so we're through with this video, and hopefully it was easy to follow for you. Nothing too complicated. And let me just go back up just to make sure. Yeah, so that's all we were gonna do in this section. So in section 5.1, we just did a one sample t-test.